It's okay, I'll hand over to these two fine gentlemen here to lead you for the afternoon.
This is going to be a bit of a buck passing exercise. It's going to be like this for the next hour and 50 minutes. Well, good afternoon everybody, thanks for coming along. And introductions. Well, you probably know Hugh through his reputation and his work at OzLabs for many years, working with some of the other luminaries of the open source movement. And he's done many talks and is very widely respected, highly respected within the open source community. So it's great to have him here. This is the first time I've done a joint presentation with you, and we'll see how this goes.
And my colleague John needs no real introduction either. Only person I know with an RFID chip in their arm, only person I've ever actually seen telnet into a car, and someone I've very much admired for all his hardware hacking. So I guess we kind of talked midway through last year and thought, well, maybe we should co-conspire and do a presentation on Arduino. So I guess here we are. It's a bit of a housekeeping matter. I've got two Arduino boards left. If you specifically got an email from me saying that I'd had one set aside from you and you haven't already picked that up, can you please let me know real quick, because otherwise it's going to go to the first and second person on the standby list. All right, so I think Jeremy Apthorn and Michael Still, I think, were my first two standbys. So if they want to avail themselves, Michael, I think, was... You got? I'm sorry. Right. Yes. So they were $50 each. So.
Well, while Hugh's arranging that, one thing I'd like to point out is that there is a wide range of expertise in the room in relation to working with Arduino, and there are many people here who have never touched an Arduino before, and I know of quite a number of people in this room whose knowledge is far greater than mine in respect to working with this sort of technology. But what we're really wanting to get out of this session is basically to expand the community of people that have had contact with Arduino and are comfortable with using it as a building block in all sorts of different projects. So what we're going to do is start from a fairly introductory sort of level and take you through some of the background of what the Arduino is all about, some of the things it can be used for, and demonstrate building blocks and techniques that you can use in whatever crazy, take over the world type projects you might have in mind. And there are a number of people here that have brought Arduino projects and other things that they've worked on, so we'll probably have a couple of little show and tell sessions along the way as well, as a bit of inspiration for some of the things that can be done. So, we need this disclaimer. This is not the sort of thing that is a problem. Actually, no, we'll get back to that. Okay, introduction to Arduino. Hugh, would you like to start off with this?
Thanks, John. So, what are we dealing with? Well, if we can juggle ourselves a little bit. That's the Arduino board. So basically, it's about that big. A number of you in the audience have them. What we might even do is just pass a few of these around, which, if John doesn't mind. The few things that are significant with the Arduino project, I guess, first of all, it's an entirely open platform in the sense that all the tools, software tools we use in order to make use of it are available under either Creative Commons style licenses or various open source licenses, hardware and software included in that. So what that means, and the boards that are being passed around are just a couple of the different variants that have been made commercially that you're able to buy quite cheaply. If we look at it from a hardware perspective, it makes use of a microprocessor made by a company called Atmel. The Atmega 168 is the specific chip that's on the boards that we'll be talking about today. It's a fairly modest part. It runs at 16 megahertz, which isn't super quick. But what's kind of nice with this particular board is some of the peripheral aspects of it. It's got the USB to serial interface inbuilt, so you can basically plug it into a modern laptop or desktop without any further ado and put firmware into it or load it. And once that's done, it's also got an onboard voltage regulator and DC inputs, so you can actually feed it off a 9-volt battery and run it in that manner. You'll see at the bottom here and at the top of the board headers where you're actually able to plug either so-called shield boards, which are like a second printed circuit board on top to expand it, or just put wires in there to link into your project. And what I'll trouble John to pass around, for those of you who have Arduino boards but didn't pick one up, we have some lovingly handcrafted LED assemblies which we'll be using in one of the tutorial parts later. Basically just a fun thing, but that will give you an idea what you can do with the headers as well. Now, if you actually have a bit of a look at the block diagram of the part, if you have a look at the block diagram of the part itself, for those of you that downloaded the tarball linked off the wiki, you've actually got a copy of the actual data sheet for the microcontroller in there, so you might want to have a look at that if you want a higher resolution picture to look at. If we look at the processor overall, it's got a 20 mega, a RISC style core which has 32 8-bit registers. It can be clocked up to 20 megahertz. The boards we're concerned with, as I said, run at 16, but the point with a lot of these systems is not high computational power, of course, it's often a low electrical power requirement. In terms of memory, there's a 16 kilobyte, I should say, flash. There's about a kilobyte of RAM and EEPROM. The reason that they provide both EEPROM and flash on the part is the EEPROM is intended for use where you have variables or parameters that you want to change reasonably regularly and be able to change on a byte or address at a byte level, whereas the flash has a minimum area that you have to erase in order to change its contents. Looking at some other aspects of the chip, the actual I/O ports down the bottom here has 3 8-bit ports which can either be configured as an input or an output, and some of them have special functions attached to them as well, so you can actually use them for analog to digital conversion, pulse width modulation, which we'll talk about a little further, and one of the ports can also be switched to be used as a serial port. That's used, of course, as part of the programming process, but also can be used in your final application. These TC blocks here are timer counter blocks, which can be used for a variety of functions, timekeeping being the obvious one, but they can be used for pulse width modulation, which is a way to control servos or to trivially generate varying voltages. But it can also be used for capturing, so you can actually measure time intervals and do that sort of thing. Up the top, watchdog timer, which can be used. It's essentially turned off by default, but you can turn that on, and what that's designed to do is force the chip to reset if your program runs away or crashes or what have you. But if you get in an embedded context where you're dealing with something that's in a black box, you often want it to be a lot more resilient than we might expect for a desktop or a general purpose computer. So we're going to switch topics a little bit, and as John alluded to, we wanted to try and I guess cover a range of levels of expertise. So there'll be electronics engineers here in the audience who will probably fall asleep for the next few minutes, but hopefully there'll be a few of you who maybe did Electronics 101 5 or 10 years ago. And I guess what we've sought to do over these next few slides is kind of give you the edited highlights of the bits you really need to remember in order to not blow things up or kill yourself in the process of playing with this sort of gear. I'm going to hand over to John for the mains bit.
Once again, absolving himself of responsibility.
Wasn't that?
No. Okay. Warning, this can kill you. When you start playing around with hardware, you can potentially be dealing with things that can kill you, particularly if you're switching 240 volt. So there are some techniques that you really need to take care of to protect yourself. And if you can, don't switch mains directly. It can be tempting sometimes to grab yourself a little relay and get out the cutters and chop an extension cord and think, I'll put a relay in line with this, and that way I can control appliances and things. That's really, really dangerous if you don't know exactly what you're doing. There are some things you can do, like using appliance remote controls, which we will actually demonstrate a little bit later on. This little device here is basically like an RF remote control for your car. There's a receiver here and the transmitter here. The idea is you plug the receiver into a power point, and it's got a relay built into it, and with the transmitter you can turn it on or off. what you can do is hack one of these transmitters and connect it up to an Arduino so that you have total isolation from the circuit you're switching. That way you're never dealing with 240 volt directly, you're only ever dealing with low voltage systems. And there are techniques like that, and also doing things like using X10 communications, which gives you a level of isolation from what you're talking to. So be really, really careful is what it comes down to. I don't want to see anybody here have tips of their fingers burnt off like I've managed to do.
For the record, I've burnt my hands as well in similar circumstances. Right, this will be a symbol that I think just about everyone in the audience has probably seen this symbol at some point when you bought memory for your computer or done something like that and probably routinely ignored. So it's a symbol for electrostatic discharge, which can kill your chips. Now, what we have here is a picture of a voltage regulator, a relatively high power or resilient part, one might think, in terms of electronic components. You'll notice this discoloration down the bottom here, and we've got a close-up of it there. That's the result of someone walking up to that part, dragging themselves across the carpet and touching it directly. So it's purely static electricity that's damaged that part. In this particular case, the fellow who's blogged this from was actually involved with the Chumby development program, and this is one of the parts they were using on the Chumbys. The point of the slide, electrostatic discharge is a bit of a insidious problem in the sense that occasionally you'll damage a part and it just won't work at all. So you quite literally blow a hole in the side of it at a die level like that and the part just ceases to function. The more insidious problem though is you can actually only partially damage the small structures on the chip, and you end up with a part that's unreliable or that will fail at some point later on down the track. So the thing to bear in mind when you're dealing with these sorts of boards, and indeed even the boards that we're passing around at the moment, is when you look at the little headers at the top and the bottom of these boards, you're basically dealing with input and output pins on the chip that don't have much in the way of anti-static or static protection on them. So it's a good habit to get into when you're working with this stuff, to ground yourself. So just touch an earthed object before you handle the boards, and I guess be a little bit cognizant of not actually zapping the things, because it's one of these things where, particularly when you're dealing in an embedded environment where you've got limited feedback from the device, if the thing just suddenly stops working, it could be your software, or it could be that you've caused some electrical or static damage to the part. Next thing I'm going to talk about is current limiting. The I/O pins on the Atmel chips have a limited ability to provide current power when you add voltage in there as well, multiply voltage in there as well, to the devices it's powering. If we look at it specifically, each pin on the device can source up to a maximum of 40 milliamps, and you have an overall maximum for the part of 200 milliamps. So what that's reflecting is the maximum amount of power you can actually pass through the power pins on the device. Why do we care about this? Well, if you were, say, trying to build a set of Christmas tree lights based on this part, you are a little bit limited in how many LEDs you're actually going to be able to hang off the part directly before you start hitting these current limitations. Reality is 40 milliamps will make a modern LED glow pretty brightly, but if you're trying to do something a bit more spectacular or use LEDs that are rated in the watt range, then you'll need to look at some sort of external switching, and again we'll talk about that further. As the second point there notes, because there's no specific current limiting, well there is current limiting on the chip, on the I/O pins themselves, but you're not really, it's more there for protection. So if you are connecting up to a LED or some other device, you should consider whether you need a current limiting resistor in there. And I guess we'll talk a bit more about that later on in the tute as well. On that note, I wanted to talk a little bit about the actual I/O pins on the device. Again, this is from the Atmel data sheet, and as you can see, this point on the side here is actually the pin that you end up connecting your devices to, which is 20 odd on the part. Device at the top is one side of the output driving circuit. This is the other side of the so-called syncing part of the output drive. The rest of it is related to when you're using the pins as inputs. It gets even more complicated if it's a pin that's there for analog side. Don't worry about that side of it. We're not going to deal with that. But if you want to have a look at that part of the data sheet, you can dig into it. Again, in practice, if we look at this from a simplified perspective, if you're using the outputs of the device, or using the pins on the device's outputs, you've essentially got a transistor at the top, which will allow power to flow out of the pin, or another one that can sync so-called sink power through it. So what this means, again in practice, is say we have a couple of LEDs connected to an I/O pin. If this transistor is on because you've written a logic 1 to the output of the port, you'll actually get current flowing through the resistor, and this LED will turn on down the bottom here. This is so-called sourcing current. I apologise to the purists because I know conventional current flow goes in the other direction. Didn't know I could do that. Alternatively, if you have a LED connector between the power rail, thank you for picking up my obvious error. But no, you did right. Yes, I should have taken that LED out of the picture. If you're sinking current through a pin, however, this transistor can switch on. You can actually sink current through. Where this can become significant is if you're driving something, connecting to something like a 7-segment display, or as we were passing around, we had a LED that has an RGB LED where you've actually got three LEDs on the substrate with a common pin. It starts to become important whether you're sourcing or sinking current in order to enable that device. I won't spend a lot of time on Charlie plexing because there's a lot of more interesting things to look at, but essentially Charlie plexing makes use of the fact that all these I/O pins on the device can either be a logic 1, a logic 0, or so-called tri-state. So when you set them to be an input, they're obviously not providing or sinking or sourcing current. So you can do some stunts here where if you turn this output on, make this output a logic 1, this one a logic 0, and leave this as a tri-state or as an input, then this LED will turn on. If you reverse that, then that LED will turn on. It's basically a stunt where if you want to be able to drive more pins, more LEDs on a minimal number of pins, Charlie plexing is a means to do that. The Charlie comes from the name of the engineer at Maxim Integrated Circuits that developed or first documented the technique. The final bit I want to touch on just really briefly is fuses and power supplies, and I guess this is sort of in a similar bent to what John was talking about the mains side of things earlier. One of the temptations that, common applications for all these sorts of things is obviously to battery power the devices. If you're going to battery power one of these boards off a little 9-volt PP3 style battery, you haven't got any great problem. That battery's not capable of generating a huge amount of current. It's unlikely to actually have anything catch fire. However, if you're looking at, say, using lithium polymer batteries or gel cells or anything like that, just bear in mind that you're dealing with batteries that can actually generate many amps and can actually get quite hot. So if you're using any sort of batteries-based power supplies beyond a certain size, I'd encourage you to put a fuse in there as well so it blows before the board does or otherwise catches fire. Right, go to the software side of things at this point. And just so I can get a quick indication, how many people have had a chance to download the tarball and the other bits and pieces that we had up on there? Has anyone got? How many of you actually got the note about having a USB cable? A much smaller. I do apologise for that. The boards didn't come with them, and weren't in a position to throw that in there as well. I'll hand the mic over to John just for a sec so I can type clearly, and I'll get a window up. What's F6 wasn't it? Oh.
There, is that what you wanted?
Yep. Cool. That'd be most. So, for those of you which have the tarball unpacked, essentially there's one change that you'll need to make to the files provided. I guess just to talk really quickly about the software environment generally, as we explained earlier on, the Arduino boards are based on the Atmega CPUs. But by default they are just a general purpose microcontroller like any other. An important part of the Arduino project was actually developing a small bootloader and some supporting software on the programming side that will actually allow you to program the device in circuit without needing to use the specific in-circuit programmer that you would otherwise require. So the Atmega environment is, in a sense, the Arduino environment, I should say, is in fact providing a mixture of a software and a hardware environment.
I just mentioned that. I personally found that was actually one of the big benefits of the Arduino platform. Prior to using Arduino, I'd used a number of other microcontrollers and development kits and things like that. One of the ones that I did quite a bit of work with was PIC Series chips and basic stamps. How many people have used PIC microcontrollers? Yep, quite a few. And they're very cool. But one of the big things that, that makes the Arduino so nice is the fact that you can simply plug it into USB, click a button or run a makefile or whatever, and your code gets pushed across onto it, and you don't have to... and the other big thing about it, this is sort of skipping back to the introduction, I suppose. The other big thing about it is that it makes things so accessible. If you want to get into programming microcontrollers in the traditional way, you'd normally have to spend hundreds of dollars for a development kit from some manufacturer, like for a prototyping kit, and then the actual boards themselves might be many hundreds of dollars extra. The environment, the build environment is often proprietary, and basically there are all these hurdles that get in your way. And one of the really cool things about Arduino is that it smooths all of that out and makes it not only low cost, but very simple to get started with this sort of stuff. So for me personally, the simplicity of the environment and what Hugh was talking about with the bootloader is a very important thing that makes it really useful for me as a very quick, rapid prototyping tool.
Yeah, I agree, and actually one of the ironies for me is I just recently, having got into the Arduino boards and realised how nice this environment is, I actually got rid of a whole bunch of microchip PIC stuff that I had been planning on doing projects with, and large reason I sold that is simply because the tools aren't open. It's much harder to do meaningful development with those parts, in my view, using purely open tools. So what we've got here is there's two quite trivial examples that made available in the tarball. For those of you that actually want to follow along and do this, the main line that you'll need to tweak is the install directory here. This needs to refer back to the Arduino 0012 directory. Now this Arduino 0012 directory is actually the top level directory of the IDE part of the Arduino tools. So in the file we asked you to download, there was a README, there's a bunch of tools like AVR GCC and a number of specific packages you needed to download and install for your distro, but then beyond that there was, from the Arduino CC website, this is one of the tarballs you should download. So you go and find that makefile and make the appropriate adjustments so that points back to your directory. That should be the only thing you'll need to do. The other thing the makefile has some basic instructions and details at the top, but essentially where most of the complexity in this particular makefile comes from is that the Arduino software environment on the, if you like, on the development side is normally run from the IDE, and the IDE sort of hides a lot of the, I guess, this behind the scenes sort of work. Essentially what's happening, if we look down, have I gone too far? I do apologise. We'll do it this way around instead. So by default, the Arduino environment makes use of so-called PDE files or .pde files. They look a lot like C, as you can see. So, but when that makefile gets executed, what's done behind the scenes is a couple of header files that get inserted up the top before it's actually passed to the AVR C compiler, and then there's a main function installed down below, and then the whole lot is compiled. So what we don't see is that within the main function that's supplied as part of the Arduino tools, this setup there's a definition to call this setup function once and once only, and then similarly the loop function, as the name would suggest gets called continually. Things like digital write and pin mode are prototypes that are defined in the overall Arduino environment. And as the name suggests, we specify LED pin 13, which happens to correspond to a LED that's on the Arduino boards by default. We set that up as an output, and there's no great prizes for guessing what the software will do itself. I'll hand the mic to John for 2 seconds so I can type two-handed, and we can hopefully demonstrate.
While Hugh's typing, just a terminology thing. What you'll see if you're looking through a lot of documentation is something like this is referred to as a sketch. So basically a sketch is a program for an Arduino. In a little while, when I do some of my demos, I'll use the Arduino IDE, which you can download free from arduino.cc. So Hugh is doing his demos off the command line. I'll do my demos using the IDE, and that will show you two different approaches basically to the same thing. Some people might have a preference for one or for the other.
Somewhere in the audience is an Arduino board, which I was actually going to demo.
Which one is it? There's a blue Arduino board? Not the red one, a blue one?
Can we do that? Yeah.
Yep. Oh, there it is.
Okay.
So, yeah.
Cool.
So, no, it's not going to retain focus size because it's... Oops.
Nope. Okay. Bear with us while we have our mandatory technical participant materials. Yeah.
Examples?
Yeah, that's cool. Yeah,
Okay.
Cool. So we did hope to be able to, thanks John, demonstrate this. We'll have a camera set up as well so you could see. But cutting a long story short, if we run make at this point, it goes ahead and compiles that, and you can actually see a certain amount of what it's doing here, where it creates an applet directory, which is where the compiled code will end up. It cats these program headers up to the top of of blink.cpp and basically builds it this and eventually runs Arduino CC to actually build it. Now if we plug the Arduino board in using the embarrassingly scarce USB A to B cables, we can now do a make upload. And that'll actually go ahead, upload it, and for those of you in the front row, there's a little blinking LED on there.
People with eagle eyes.
With people with eagle eyes, thank you. As John said, this is all done, all this I've just demonstrated has been done from the command line. That make file can obviously be adapted to be used for any other sort of applications, but the rationale being that we felt many of our fellow open source developers tend to prefer command line based stuff. I'm sorry. So the reason I want to demonstrate the command line first is essentially just to show that it's there, because out of a realisation that many of us do prefer those tools. Yeah. Sorry. Cool. We love OpenOffice. Right. Okay. Right. So for those of you following along, we've got some blinking LED. Next thing I want to talk about just real quick was some programming considerations. This is by way of, I guess, the first example of fairly common idiom, obviously in C, is a simple loop. And you notice in this particular instance that we're using an integer as the count variable. Now that will work, but we've got to remember we're dealing with an 8-bit microcontroller here, so as soon as you start declaring integers, which are 16 bits, you start to add an awful lot of overhead. So there's a better alternative in this particular case, because we don't need to count very high, is to use bytes. So for those of you that come from more traditional programming environments, I guess, or programming backgrounds, just bear in mind that you really are dealing with a very, very small in terms of computing resources part here. So if it doesn't need to be an integer, don't make it an integer. You've got limited memory, you've got limited register width. All the registers are 8 bits wide. So basically try and fit things into the smallest data type you possibly can. And I guess those of you that come from Java programming backgrounds, this will maybe just a lost cause entirely, I don't know. But the next thing on the demo is, which we hopefully will be able to see from the back, is the RGB LEDs. Now these are just intended as a...
I can switch to cheese on a different...
Yeah.
That one, it goes in there, doesn't it?
Yep. So all the little LED assembly that we passed around has an RGB LED, so LED with a red, green and blue LED. LEDs all in the same substrate, which we can...
So if you're wanting to plug this in, you've got one of these little tricolour LEDs down there. Basically the way it works is that it plugs in, I've got to find a good angle here. Don't get seasick. So it plugs in so that it's connected to ground. The shielded cable here goes to the ground pin, and then it's using 3 of the outputs, in this particular case, 9, 10 and 11 I think. So if you plug it in that same position, you should be able to run the example code that is in the participant materials.
Cool, so thanks, John. So if we go back to similar sort of thing here, we'll just run make to build it. It's already built, and if we do a make upload, this one's actually bright enough to see the back. Sorry, question please. So it's me being lazy actually, because the part on the Arduino, or AT, that mega part being used on these boards is a slightly later revision than what I've got the make file configured for. So it's just me being lazy and not updating the, part of the make file you specify what device, what your target device is. They're close enough match that it actually works in practice, and I just haven't gone in and tweaked it. So sorry about that. Please. Yes, that was why the question was, were the output pins that we're using to drive the LEDs ones that are connected to the pulse width modulation outputs, and they are. We're not actually using it in PWM mode. I thought that would be a good exercise for the gentle readers, and there's actually some example code. Actually, not at this stage. We're not actually. They're all just on or off. So if we have a quick look at that code, yeah. It's not the last word in elegant C by any stretch of the imagination, but define the pins up the top, a little function, so you can actually set to initialise the relevant pins as outputs, set the LEDs on and off, and then down here is the colour cycling. The PWM outputs on the chip actually would allow you to change the LED intensity through quite a wide range, but there's a number of examples in the Arduino code itself that which John will talk about. Yep. Right. Yeah, we go back to. Yeah.
It's on a different desktop.
It is.
So
sorry, man.
That's all right. Did you want?
I think we're back to the.
Where are we? Way down here somewhere. About here.
Yep. Okay, so that was the final demo I wanted to run with the board here, and then John's got some demonstrations on some other aspects like digital input and so forth. So I'll hand over to.
Okay. Thank you. Also, one thing I'll just show at this point is how inconvenient it is not to have a lapel microphone, and that's okay. That'll be fine. And the IDE that you can download. So this is a little sketch that we'll use in a moment. the IDE basically is a convenience thing. It gives you an editor for your code directly, but it also provides direct upload. So instead of running make when you want to build your program, you click here, which is verify, which is basically make. So by clicking that, that's just compiled the bytecode that needs to be pushed across to the board itself. And then uploading is just a matter of clicking upload. So this gives you a handy little environment to do development in and push stuff across to the board itself. So personally, I spend most of my time using this. I think Hugh uses the command line equivalent, but they both do the same thing. So, sorry, the question?
Is there an emulator at all?
For the hardware? Yeah. That's a good question. I don't know. Does anybody know if there is a simulator for the hardware? Something in Debian? Okay. All right, so the short answer is yes. Sorry, I don't know any details about it though. Okay, digital input. What I'll show you for this is a little board that I set up. This was actually from a talk at Myth TV, mini-conf. This is just an example of how to take straight digital input, so reading a value as to whether something is on or off or not. In this case, what I've got here is an infrared receiver and an infrared transmitter. So this is a light beam, typically like a door minder sort of thing that you would find in a shop to set off a buzzer when you walk through. On the door minder, on the receiver, it's got a little relay. So what I've done is connected, not that you can really see anything much from there. Please excuse me a moment while I plug all this together. Not sure how clear this is. Not very, I think, is the answer. But basically what I have here is an input which is being pulled to ground by a dropper resistor. And I have a 5 volt as well going into the other side. So what I can do, actually I got that around the wrong way. So what happens is that when this input is shorted, the state will change on the input from low to high. What was it? Pin 2, okay. Thanks. So just looking down this code, basically what we're doing is defining an output pin as pin 13 because that's got an LED already on it, an input pin. So pin 2 in this case is the one that we care about looking at the status of, and an initial value, and yes, I should be using a byte, not an int. Because each of the digital lines can be used as either an input or an output, what you need to do is declare the mode that you want. In this particular case, what I'm doing is saying I want to declare LED pin as an output, so that's pin 13, and I'm declaring the input pin, which is pin 2, as an input. That then puts the hardware into the correct state inside the machine. And then in this case, this is something that is a really handy little technique. We're doing serial begin 38,400. And what that does by default is there are a couple of pins that are reserved for serial communications. On these boards, they have a USB port. There are other boards that have Bluetooth or RS-232 interfaces on them. You can use those pins for other purposes, but it often ends up getting messy. So pins 1 and 2, generally you don't end up using in your own projects unless you unless you really need them. So by doing serial begin 38,400, it's telling it that it needs to set up serial communications at 38,400 bits per second. That then allows us to either read from the serial connection or write back out to it a little bit later on. So in the loop, what we're doing down here is simply saying val equals digital read input pin. And that is as difficult as it gets, basically, to read a digital value on an input. With that, what we're doing is assigning the value coming in from the input, so it'll be either a 0 or 1 or a high or a low or true or false, into that variable, and then just doing a simple comparison. And then if the value is high, we're sending the value 1 to the serial port. If it's low, then we're sending the value 0. And then just sleeping for a while, and then going around the loop again. So the end result of this is that if we're watching the serial port, we should be able to change the state of the input and have that reflected in the value being put back out the serial port. So conceptually extremely simple, but these sorts of things are really useful building blocks in your own projects. You'll typically end up doing a lot of work reading and writing I/O pins and a fair bit of serial communications as well if you're wanting to monitor the status of the board. Actually, something I should point out that we didn't really mention early on. These boards are typically used connected via USB, but they work just as well totally standalone. You don't need to have them plugged in. Because this is a complete standalone microprocessor, if you have power applied to it, it will run the program that is in memory and it will just simply keep executing. So if you have an application where you don't really need to have interaction with a computer, you just want some kind of pseudo-intelligence built into a device, and you can set that up in your software, all you need to do is connect power up to it, and once you've got the code set up and running, it'll just keep running forever. Yes? It depends on, the question was, will they switch between USB and external power? They have two different inputs. They can either leech power off the USB, or there is a plug, a socket on it which you can put power into. On the early boards there was a little header, you had to switch it manually. With the later boards they will auto-detect, so it just does it, you don't have to care about it. Basically, Arduino in terms of its functionality hasn't really changed. It's gone through a number of generations over the last couple of years, and the boards have got better and better. And this is actually a great example of some of the tweaks that have been done to it. Functionally, the boards still basically do the same thing, but they've made these little improvements so that you can take code that was written on an Arduino a couple of years ago, put it on the latest board. The architecture is the same, it'll work. But then little things like the fact that it auto-detects where its power should be coming from or what make it nicer. So the advantage you get with some of the later boards are those little rough edges that have been smoothed off. So let's give this a try. I don't think this is loaded on the board at the moment. So yep, if you can plug that in here, that would be great. So when it powers up, I'll click upload. And also, just to explain this boot sequence a little bit, when the Arduino first powers up, what it does is watch the serial port for a few seconds. I think it's 6 seconds by default. I can't remember the detail. Does anybody know how long it is? I think it's about 6 seconds anyway. What it's looking for is a new program to be loaded and executed. And during that boot process, it'll sit there waiting for a new program. If it finds one, so in this particular case I uploaded onto the board, I had the IDE ready to upload, it's now accepted that new program and it should right now be running. If it gets to the end of that period and it hasn't seen anything, it simply starts executing whatever was stored in memory last. So each time it powers up, it'll just go through that little cycle. Now if we switch over to monitoring, this is also one of the other little convenience factors of the IDE. This window down the bottom is a status display, and it shows you, I'll pull it up so you can see it from up the back. It shows you what the IDE has just been doing. You can also put it into a serial monitor mode, and in this particular case, we've got to match the baud rate. When I did the serial setup, I said to be 38,400 bits per second, and so what we're doing now is outputting, yeah, thanks Hugh, you can plug that in. What we're doing now is seeing that it thinks that the relay is currently turned off, so it thinks there's no value coming in from it. So if you now stick that down in front of it, the relay will click, and we should start getting some, damn, demo fail. And in theory, we should start getting some 1 values coming back if it's seeing that the thing is connected. Relay chatter, that sounds like fun. One of the other differences between some of the early Arduinos, and there are a lot of them around, so it's worth knowing these sorts of differences, that, yeah, I think I've got a, I don't think I've got that set up correctly, that when, in the early ones, they would only load a new program as part of the boot sequence. So once it's booted, you have to reset the Arduino or remove its power, like basically power cycle it, if you wanted to put a new program up onto it. So you couldn't have a program running, having it sit there and just come along and click upload and have it do it. With the latest version of the bootloader, you can do that. This particular board I'm running right now is an oldish one. It's an Arduino NG. It's a couple of years old. And so if I tried to do an upload now, it wouldn't do anything. And we got a 1. That was probably just a weird glitch. Is it into 5 volt or ground? 5. Oh well, it's not worth spending too much time trying to debug this. For those of you that came to the Myth TV mini-conf, you would have seen it kind of working and controlling Myth TV. Hey, one person saw it, that's cool. Alright, so, where were we? What next? I'm very confused by keyboards that are in QWERTY layout. Where did that go? There. Okay, so that's basically as simple as digital input is. It's just reading from whichever nominated input you want to take the value from. What you probably can't really see because the camera doesn't show it very well is the way the input works. Because the input can be either in a high state or a low state or undefined floating, the typical way that you would work this is you have a resistor, like a 10K resistor, which I have in this case, which is connected to the input and to plus 5 volts, so that in the absence, or to ground, so that in the absence of any other input, it's going to be at a defined state. And then what happens is that you connect to the other supply rail, so if it's being pulled down to ground, then what you can do is send 5 volts into it directly, and that will pull it into an upper state. So it's always defined as being either low or high. You don't leave it in a floating condition. Output buffering. Did you want to mention this? Or? No. Okay, output buffering. Another demo to fail. As Hugh mentioned earlier, the outputs on the Arduino are very low power. They're basically 0 or 5 volts, and there's also some PWM, which we'll get to in just a moment, but that's a separate issue. But they can only sink or source a very small amount of current. With a typical project like a robotics project or whatever it is you're wanting to interact with, you'll often want to switch larger, either higher voltages, you don't just want a logic level 5 volt, or you will want to deal with higher currents. And the Arduino really can't do that. So in order to protect it, you need some form of buffering. The most common way of doing this is with a transistor. So what you do is take the output, feed it into the base of a transistor, and you use that essentially as a little electronic switch. We won't go into that right now. There are plenty of resources online to show you how to do that. What I'll show you now, and also the other thing I should mention is that there are a whole bunch of techniques for doing this, depending on what it is that you're wanting to interface with, whether it's high voltage or it might be high current but low voltage. There could be all sorts of different types of dangers involved, so you really need to use whatever is appropriate. It might be that you have a long cable run, therefore there is a potential of lightning strikes and you need to have some isolation against very high voltages on the line. You really need to pick whatever technique is appropriate for what you're working with. I find that for the kind of projects that I do, most of it is taking some existing appliance and ripping it apart and connecting it up to things. Basically what I want to do most of the time is simulate a button press. If there's a device like this remote control, which has push buttons on it, I want to be able to simulate pressing that button but have it done under software control. One of the easiest ways to do that is to use read relays. These are one of my favourite things. They're about $3 or so, $3.50. It's a little 5 volt device. It's basically the size of an IC, but it's a very simple little relay. And the really cool thing is that you can get them in a 5-volt version, and they draw, typically it varies from manufacturer to manufacturer, but often around 20 milliamps, which is a really tiny amount. If you consider this is actually an electromechanical device, it's running a coil which is then physically moving an arm. So you've actually got mechanical isolation there. It's not just electrical isolation. The fact that it can do that on 5 volts with 20 milliamps is pretty impressive. And what that means is that you can connect these directly to the output of an Arduino and it will drive it without any problem whatsoever. So that's often what I do. So this particular, I'll show you this little assembly here. This is intentionally crude because I want to show how little it takes to make this happen. If you've got a physical device that you want to interface with, it really only takes an Arduino and a couple of parts and you can do this. Basically what I have here is the read relay itself, and on one side it has connections to the coil, that makes it better, and which is the input, and on the other side it has connections to the output. At the other end of that cable is just a little header that plugs into the Arduino and is connected to a ground, and then I've got 2 outputs. I've got 2 read relays here. So what this little simple assembly, basically a header and 2 little relays, I can plug straight into an Arduino, and we can now use that to wire across push buttons or whatever else we want to control, and isolate ourselves from it electrically, but still be able to control it. Now we need to change tapes, I believe, so we need to just stop for a moment while that happens.